Welcome to the Neural Implant Podcast, where we talk with the people behind the current events and breakthroughs in brain implants in an understandable way, helping bring together various fields involved in neuroprosthetics. Here is your host, Laden Yurachek.
Hello, everyone. Welcome to the Neural Implant Podcast. Today's guest is Dr. Melanie Ecker at the University of North Texas, and she is an assistant professor at the Ecker Lab's Smart Polymers for Biomedical Applications. And it's funny because I met her before she was a professor. And so this is really cool to see somebody grow into this position of having a lab and to get the audience on board. We were in Minneapolis at the Neural Interface Conference, NIC, in 2018, and I thought that was an amazing conference. And we were on some roof with Dr. Walter Voit, a previous guest of University of Texas of Dallas, and TK Kozai, and just a bunch of other big names. I thought it was really cool, and we were just all having a beer. And I remember Dr. Ecker was there as well, and looking for a position. So, pleasure to have you on the show. And do you want to introduce yourself and talk about some of your work?
Absolutely. Thanks for having me here. And is it really so long ago? 2018? Wow.
4 years. Isn't that crazy?
Yes. So I guess you already introduced me, but I can, say a little bit more about myself. I'm a chemist by training, actually, kind of slided into bioengineering by accident because I ended up in Walter Voigt's lab. I was looking for a postdoc position because my background is in shaped memory polymers, and I knew that he was working on these cool neural interfaces using shaped memory polymers as substrates. And I really wanted to learn more about it. So I reached out to him and, ended up in his lab as a postdoc. 4 years later, I got my own position, my own lab. As you already mentioned, I started at UNT, which is in Denton, North Texas, and have my own lab now where I still continue to work with shaped memory polymers, some of them still for neural interfaces, some of them for completely other biomedical applications. But I guess since this is the neural talk here, we will mostly be focusing on the neural interface side of things of my lab.
Excellent. Maybe let's introduce what are shaped memory polymers and how does it relate to neurotechnology?
Of course, absolutely. So shaped memory polymers are sometimes called also smart polymers. The beauty about those materials is that they can remember a previous shape. So you can imagine it like you have a plastic material, you can deform it and bring it in a temporary shape, meaning you can just collapse it, make it very small. And then if you insert it into a body, for example, then it can deploy and remember its original shape, for example, a flat shape or a curled shape, whatever shape you want, you can program into those materials. Especially when you think about neural interfaces, you could use them for self-curling nerve cuffs, for example. So they are flat initially, but then if they get in contact with the body temperature, they start curling up and then thereby curling around the nerves by themselves. That might be just one of many applications for shaped memory polymers, also in the sense of neural interfaces. Another way how we use those materials is to make use of their softening capabilities, which is kind of a side effect of the shaped memory polymer. So in this sense, we're not using the shaped memory of the materials, but just the mechanical and thermomechanical properties of those materials. That was a key of those self-softening shaped memory polymers that are the baby of the Voit lab, basically. I guess you mentioned, right, you had Walter on the show before?
I think he was actually guest number 1, if I remember correctly.
Oh, really? So he probably also talked a lot about the self-softening polymers. But so, there are some applications where we actually want to make use of the shape memory, right? The capability of the materials to remember a previous shape, to deploy or change the shape in situ. But for many other applications, again, we just use kind of a side effect, which is the softening of the material.
Yeah, definitely. The mechanical mismatch between hard devices and soft neural tissues is a big thing. But at the same time, you want to be able to have the surgeon be able to handle it and not have it just be jelly in their hands. That's a huge thing. So what were you working on in the Voit lab? And and then how did you manage to, and then now what are you working on, I guess?
Mm-hmm. So since my background was polymers, shaped memory polymers, so naturally I started working on the polymer side of things in the Voit lab. I was further developing some of the materials that were initially developed by Dr. Taylor Ware. And so we used, or I don't know, just made different iterations of the material. I was further investigating what the material is actually doing. One of the bigger things that I was onto was to develop materials that are hydrolytically stable, because, right, for all those neural interfaces, for most of them, we want them to be long-term stable. That is always, right, one of the things people are talking about, how durable are those devices, how long will they last? And in the sense, I was working a lot, towards solving this issue. First of all, how can we make those materials durable, how they are long-lasting without degrading inside the body? And also the whole devices themselves, right, packaging, insulating layers. We were looking at adhesion layers, things like that. So my part was more on the material side of things, not so much on the devices, even though I learned a lot about microfabrication and also all the animal work. Because while I was a postdoc in the Voit's lab, I was also, I would say, part-time postdoc of Dr. Joe Pancrazi's lab, because there was a shared grant between those labs where we were looking at also these softening polymers that could undergo different degrees of softening, because we wanted to look into how soft is soft enough. So we had materials that did not soften at all to have as a benchmark to control for, and then some that got 10 times softer, others that got 100 times softer inside the environment. And then we were looking into how the rats responded to those materials. But again, my part was the materials development here. But it was really good to see and work with all the other students to see how the animal work looks like. I was attending several surgeries, recording sessions, things like that. Yeah, it taught me a lot. And then I guess to find the segue, how do I start my own career? Good question. While I was a postdoc, I was 2 years in when I figured out that, well, doing research is what I like. Working with students is what I like. And being in bioengineering was really something that I like, because working with materials and being able to do something for mankind, if you will, to kind of advance healthcare and medicine with the knowledge about materials I had, this kind of became my vision. And if I do an independent career, I really want to still work with materials, polymeric materials, and use them for biomedical applications. And since I started to work on neural interfaces, I also wanted to continue to work on those, at least for one thrust of my lab. And I had the idea that, hey, currently not everyone, but most of the people are focusing on the brain. It is important. I do understand that. But I thought that there are already too many groups focused on that. And with that, also funding, right? Everyone is just fighting for the same pots of money. I thought there's more, right? There's more than just the brain. There's also the second brain, meaning our guts. And within our guts, there are also so many nerves, the enteric nervous system, essentially. So these are the nerves that are in our guts. And I was really interested to learn more about those nerves. And I was asking myself, hey, why is no one looking into those nerves? And I think the simple answer is that they are inside our intestines, right? And the intestines are very soft and squishy and always moving tissue, which makes it really hard for conventional neural interfaces to interface with, right? Just thinking about the very traditional probes like the Michigan probes, Utah arrays, right? How do you want to stick those into the guts? Almost impossible without stabbing them, basically. But then I thought, I work with polymers. And now we have so much design freedom to make substrate that is suitable to interface with the intestines. And this is how the whole idea started, to work on gut probes, how we call them in our lab. Yeah, this is one of the driving ideas that we have in our lab, to really make those probes working, to develop these as a technology platform that we can one day hand them out to the whole research community, and everyone can look into our intestines and see what's going on there on the neural front.
Yeah, that's really interesting, actually. Hey guys, just a quick pause to talk about our show sponsor, Ripple Neuro and Neuromed. If you're a scientist looking to get the best quality data possible in your animal and human ePhys experiments, then talk to Ripple. Get a complete solution for your neuroscience research application backed by dedicated support. Be sure to tell them you heard about it on the Neural Implant Podcast. That will really help us out. Thanks. Now back to the show. First of all, I really like this idea because this gut-brain axis is becoming more and more popular. People are becoming more aware of its importance. But that's probably a pro and a con with the pots of money that you were talking about, like going after the same pots of money. Like they could be all going after the same pots of money, but the thing you're going after, that there might not be a pot of money yet. You might have to create that pot of money, I think. But yeah, this is really interesting. And so is it really the problem that these old-fashioned neural interfaces move too much with it, or they're too stiff in comparison to these neurons? And then are these neurons on the inside or the outside of the intestines? Is it easy to access, relatively speaking?
Very good questions. I guess we're picking on the first thing that you mentioned, the pots of money. I think that's currently maybe a problem to really find the right pots for this. There seems to be some interest, but yeah, it's still a little bit hard to convince people that is a good project to work on. But to answer your other questions, there are different things when you think about how can we attach a neural probe to the intestines. It's not only that it is a very soft tissue, but it's also moving. We have gut movements, and that means we need to have a material that is very stretchable so that it can stretch with our intestines. And stiff probes like the silicon-based probes, they cannot move with the intestines. So if you attach them, they would probably break or just detach. That's one thing. So this is where I think, right, having a material substrate for our neural interfaces that is soft, that is so that it can comply to the complex surface geometry of our intestines. At the same time, something that is stretchable to withstand the gut movements would be, very beneficial as an interface. We're now going to your second part of the questions, where the nerves are. That's getting a bit more complicated because inside the intestine, there are different layers of neurons. And some of them more superficial, others are very deep inside. So having these surface probes will also be a bit challenging to see, okay, what types of nerves do we really listen to, and to do some spike sorting there to really learn more about what's going on there. My vision for now is to develop a device as a prototype or as a vehicle that we can learn more about all those processes. But I guess, and I know it won't be easy, that's for sure. We were also thinking about, hey, maybe we can have a device that we can slide inside, that's then embedded inside those neurons inside the gut. But we did some preliminary work, some pilot recordings from rat and mouse small intestines, where we placed these softening probes just onto the surface, and we were actually able to record some signals. It's still not 100% sure if that was neural signals or muscle signals, because there are also a lot of muscles inside the intestines. But we think that we were able to get signals from the neurons based on the spike, the intensity, and then the span of the spikes. But again, so that's all things that we need to explore. But in order to do, need really good devices, right, to be able to go this avenue. And when you think back how everything with the brain started, in the beginning, also no one really had an idea what they were doing. And I guess still for some of the devices, people don't know what's going on there. But yeah, I'm excited to go a new avenue and to be one of the pioneers into a new field.
Yeah, that's pretty exciting. And then, as we talked about at the beginning of the show, you have a new lab. And before we started recording, we were laughing at the very bad timing of it all. So, do you want to go through all the bad timing and what stage you're at right now?
Yeah, sure. I started in fall 2019 as, brand new, right? Assistant professor, new lab, new everything. And at the same time, we also moved into a brand new building. So nice new labs, but completely empty. So what's the first thing you need to do? Well, purchase equipment and hire students. So being someone, right, completely new lab, new equipment. So that took some time until we got all the equipment in. Once we had everything there, so then for another half year, something, we couldn't do a lot of research because of that. Then having new students completely untrained in the field. They had an idea about polymers, but not so much about microfabrication. So that's also a learning curve. So it took probably the first year or so until we could start doing actual research. But I don't want to complain too much. I'm not the only one. So everyone had the same thing happening at the same time worldwide. And there were some other new investigators who had the same challenges. And then luckily we all got tenure clock extension for a year. So that would hopefully mitigate some of that. But yeah, some struggles at the beginning. But
okay. And so now you're in the process of applying for grants and applying for research projects, all this kind of stuff, right?
Yes, absolutely. I was applying for proposals or for grants all the time, right? Writing proposals all the time. Currently working on another one right now. Yay! Summertime, best time of the year, being productive. But yeah, working on proposals for these gut probes and some of the other projects we're working on, and then getting students trained. And then, well, we talked about it earlier. I was a postdoc at UT Dallas where we had the very fantastic clean room. Now being at UNT, we do have a clean room, but it's not as fancy as the one that's available at UTD. So that's also a little bit of a challenge to translate some of the fabrication techniques we use there to, well, the equipment and tools we have available here. So this is why we are now also going a little bit different route. We still try to get our probes on these very soft and stretchable substrates made in the clean room using these traditional microfab techniques. But we're also going a second route where we now have developed our own 3D printer in the lab so that we can print conductive polymer composites that are also stretchable directly on top of our substrate. That way, right, we don't need the clean room, and then we have all-in-all stretchable devices and don't rely on any metal traces and serpentine shapes, things like that. So now we're doing these kind of two approaches in parallel and see in the end which one is the better one.
Okay, that's actually something I was going to ask, was about the conductive parts of these flexible devices. So it sounds like it was just kind of metal and then maybe some wavy pattern or something which would allow it to stretch a little bit more. But you're moving, so that's how it was before, but now you're moving to these conductive polymers?
Yes and no. So we still do this approach in parallel. Some other prototypes done, and right, maybe we don't need them as stretchable, but time will tell. But since we do see that there's a limitation if we use only metal traces, because right, they will break even if we make them in wavy and serpentine shapes, we were thinking, how can we make the probes super stretchable, if you will? And for now, the limiting factor are those metal traces. So what if those traces are made of polymers? We can use conductive polymers themselves, like PDOT, things like that. But we think is a better approach is to have conductive polymer composites. Now we are playing around with different conductive fillers that we put in the same polymer that we are using as our matrix for our substrate material. And then we are printing those now on top of our substrate materials. And then it's basically all the same materials, all encapsulated in the same material. And then, yeah, we can make these very stretchable overall devices. And the beauty about the intestines is also, right, in comparison to the brain, our probes, the electrode, they don't need to be that tiny. So we can work with bigger features, making those things in the lab environment. So yeah, that's another advantage, moving away from the brain.
Yeah, that's pretty cool. And then maybe you don't even need what you were saying before, the microfabrication. Maybe like you're saying, even a 3D printer might be enough. Millimeter size electrodes or something like this, which would be enormous for anywhere else, might be big enough here. Yeah, that's really interesting. So actually, I don't know if we had talked about it, but this is actually something that I'm studying, is the longevity and the survival of these electrodes in the body. And is this something that, especially like these 3D printed parts, the conductive gels and conductive polymers, is that something that lasts long in the body, or is that attacked or dissolved pretty quickly, or how does that work?
That depends on the material we are using. We can do both. Either we can work with materials that are very stable, or we can work with materials that are degradable. You could also imagine that we work or make devices that dissolve over, 6 months, and then they're gone. No need for removal. It really depends on the application in the end. Since my background is polymers, chemistry, I can go to the drawing board and really design a material that is tailored to the application we want. For now, we are working on materials that are stable, and we do have degradable materials for some other applications. But the other materials, since they also have similar properties in terms of stretchability and things like that, we could easily use those for the bioelectronics as well. So again, right, it really depends on what you envision. What do you want to have? Do you want to have a degradable bioelectronic device, or do you want to have something that is long-term stable? You can do either.
That's pretty cool. I always see that as a little bit of a magic. We had one postdoc in our lab who was a material scientist, and it's always amazing to, like you were saying, go to the drawing board on the chemistry and just design something. To me, it's, I don't know, might as well be talking magic or something like that. But yeah, great. A fun question I like to ask: if you had unlimited funding, what would you do with it?
Wow, hire tons of students and be finally able to pay all my students and then purchase a lot of equipment. So that's the thing most of the new investigators have. Well, we get some startup money, which is good, but it only can buy you so much equipment and students, men and women power. So I really would like to expand on the equipment I have. So I have some neat ideas for mechanical and thermomechanical characterization tools that I definitely would need to purchase. I would stock up our clean room so that we can actually make devices there. As of now, we don't even have a mask aligner, which is sad. I know there's some, they got a grant. They said we should have it by June. Now they say maybe September. But anyway, so yeah, I would buy a lot of equipment and a lot of students. I mean, I already have so many students in my lab, but sadly, I can only pay 2 of them. The rest, I will not say slaves. You don't say that, right? No, they are all working in the lab because they like working with us. They like working with polymers. They like to learn things. So we have students from all levels, from high school students. One thing that we do have at UNT, which is a very neat program, it's called TAMS. These are gifted high school students which is an early entry program to college. So for the last 2 years of high school, they actually take college level classes. So they also love working in the lab to really get their hands dirty and learn research. So we always have some of the TAMS students in the lab, undergraduates, graduates of master students, PhD students, right? And not all students get paid, but we can do research for credit. We do summer internships, things like that. But yeah, if I had more money, I would love to pay all my students.
Wow, that's actually sounds pretty good. And you said you had a pretty big lab. How many people were in the lab?
12 students.
12. Wow. That's pretty great. What, for somebody who's so early stage like you are, it's surprising to hear that that you have that many students. And it seems like you have a talent or something with being able to drive these volunteers. And yeah, what do you have any tips for how to do this, or maybe how to recruit, or I don't know, something like this?
No, no, I don't know. It just happened. I guess some reasons might be that when I started, I was the only female tenure track professor in our department. So the majority of the students in my lab are female as well. So yeah, that's one thing that they were really happy to finally have a female professor that they could go to. This is one thing. And then in addition to that, probably also the research that we are doing, because it's a little bit different to what else is going on in the lab. And then, I don't know, just be open and nice to students. I guess we're all nice to students, but I don't know, maybe what I hear a lot is that I'm just an approachable person. So I'm open, and yeah, I don't know what to say. It's just, right, I like students seem to like me as well, which is good.
Maybe that's it, is that you like the students and they can sense that.
Maybe, hopefully.
Yeah.
And then, right, what also helps is bring donuts to group meetings.
There it is. There it is. Bribing them and making sure that they keep showing up, even if they're not getting paid. They get a full stomach. That's cool. Well, Dr. Ecker, this has been excellent. Is there anything that we didn't cover that you wanted to mention?
I don't know if there's anyone out there who is funding research like the research we're doing in our lab. Please don't hesitate to reach out. We're always happy to work. Just as Yoga said, I'm trying to get funding, but yeah, I don't know. Otherwise, if there's anyone who thinks that's cool research, right, and you have interest in working with us, again, feel free to reach out to us. We're always happy to collaborate and work with other people. And if you have some ideas or think, wait, what they're doing makes no sense, please reach out to me as well. I'm always happy to discuss ideas or concerns you may have about the things we are doing.
Excellent. So if anybody has any comments about what you're talking about, then definitely reach out. Dr. Ecker, this has been excellent. Thank you so much.
Right. Thank you very much for giving me the opportunity here.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.